Hello and welcome back. Today I want to continue working on the tube filament DC power supply by building and testing the circuit we worked on last time. So it will be important to verify not just that it can supply 6.3 volts of DC, but also we need to check if the various tweaks we added are actually helping, like the soft start and the current reducing inductor. So if you're curious, then keep watching. Let's start things off by reviewing the schematic we came up with last time, and what are the various details that were implemented. So here is the final schematic that I came up with. Starting from the left side, we have our input going into our rectifying bridge. So this is built with 2 Schottky diodes and 2 transistors. There's no protection elements on the transistors because we're working with very low voltages. So if you would be working with higher voltages, you would need something to protect the gate source of the MOSFETs. Next, we have something that looks like a pi filter, but isn't really. So we have some very large capacitors after an inductor, but before the inductor I only placed a small 10 microfarad electrolytic capacitor, and the purpose of this being to prevent any sort of oscillations. So this capacitor already has some built-in series resistance, so that should be sufficient. We don't really need a dedicated series resistor here. And finally, we got our LDO section. So I'm using the linear technology LT1529, and this comes in 3 versions. You should be using the adjustable version. So with this set of resistors, you should be getting 6.38 volts, but well, you can work on the feedback network a bit to be closer to what you want. I'm using the fixed value 3.3 volt version, and this is not recommended, but this is the component that I have. And well, other than the resistors, in the feedback network, we have this capacitor, which should provide us with a soft start effect. So at startup, the capacitor should be discharged, shorting R1, setting the output voltage to the internal reference, 3.3, and then as the capacitor slowly charges, the output voltage should slowly rise and stabilize at around 6.3. Now, most of the large capacitors in the circuit are electrolytics, so aluminum electrolytics. So I also added C7 and C8, 2 ceramic capacitors, 470 nanofarads before and after the regulator, just to provide some high-frequency decoupling, since ceramic capacitors have much lower series resistance and series inductance compared to aluminum electrolytics. Now, coming to the layout, well, nothing really special. This is quite a simple circuit. On the upper side, I have the supply input going into the rectifying bridge. This goes through the large inductor. Then we have the 2 large capacitors, and then on the bottom we have the linear regulator with its heatsink and going into the output. Now the only interesting thing worth mentioning is that from the input up until the large electrolytic capacitors, I used very thick copper traces, and then after the linear regulator I went with relatively thin traces. And the reason behind this being that up until the capacitors you have your rectified AC coming in short pulses of high current. We're expecting something in the range of 5 amperes. But after the capacitor going through the linear regulator, you are expecting constant current of about 1 ampere. So since we can't always have thick traces everywhere in our design, it's always important to identify where exactly special measures are actually needed and only implement them there. One more thing to talk about before looking at the complete circuit is the inductor, the 200 microhenry 5 ampere rated component. Or at least that's what it should be. Anyway, this needs to be a physically large component so that the core material does not saturate, and you also need relatively thick wire so that you have limited series resistance. One more thing to point out is that you want a closed magnetic circuit inductor. So commonly, high saturation currents are obtained with large gaps in the magnetic circuit. But these also lead to large external magnetic fields, which generate noise in the circuit, and we don't really want that. Of course, the component that we need is probably commercially available, nowadays on some sort of ferrite core. But since we're working with relatively low frequencies, in the range of 50 to 100 Hz, you don't really need ferrite. You can work with good old steel. So you can use an iron core transformer for this purpose. And that is exactly what I'm using today. I had this old core lying around and decided to put it to good use. And everything put together looks like this. We have the large capacitors, inductor and heatsink dominating the board. All of the other components are just dwarfed by these. I added the heatsink only for the linear regulator, the LDO. The elements of the rectifying bridge are left uncooled, but we'll be looking at this in a bit more detail later. So it's time to test the circuit out. For that, I prepared this setup in which I'm supplying the board from my power transformer, which is off screen. Current is passing through the current probe, which I'm measuring on the oscilloscope. Then the input voltage is being measured by two probes, so differential measurement. This will show up as our white trace. And then on the output I have an active load with a voltmeter and ammeter measuring what's going into the active load. And then I have a final remaining channel with which we can probe the circuit. So let's turn it on. And nothing bad happens. That's always a good sign. So nothing blew up, there's no smoke. We see our input current, and we can also see at the output that we're getting about 1 ampere set by the active load and about 7.13 volts. Wasn't it supposed to be 6.3? Well, after a bit of poking around, couldn't really find what the issue is. Might have something to do with the regulator being of a fixed output voltage type and not the adjustable version, or maybe there's some dirt on the PCB which is affecting the feedback resistors. But anyway, if we add an extra 180 kilo ohm resistor in parallel with the upper resistor, we do get 6.33 volts, which is good enough for our needs today. So now let's start probing through the circuit a bit, see if everything is working as planned. Well, the voltage didn't work as planned, but let's hope everything else does. So first of all, let's just remove some of the traces. So if we look at the voltage after the rectifying bridge, we see this weird shape. So this is a waveform that has a peak-to-peak value of about 1.04 volts, maximum of 9.04, minimum of 8. And if we look at what's present after the inductor, we see a much nicer waveform. So this is what we're expecting, charging and discharging of an inductor. Peak-to-peak value 960 millivolts, so slightly lower. Maximum value 9.12, minimum 8.16. So the waveform after the inductor is much smoother than the one before, and it's slightly larger also. And well, finally, if we look on the DC output, it's nice and clean. So just to check this, I set the oscilloscope probe into AC coupling, and we can see that at 10 millivolts per division, we barely see any ripple. So this is mainly coming from the noise from the circuit and well, my probing technique. Next, since we bothered making an active diode, we also need to check that. So for that I set the oscilloscope into the average mode, so to get some cleaner waveforms. And well, if we probe the voltage after the rectifying bridge and compare it to the input voltage, so using the cursor keys, first of all we can see that the input voltage isn't really a sine wave. Right when we have a peak current we have a dip in the voltage, but regardless, based on the cursor measurements, we have about 0.36, 0.4 volts of voltage difference between input voltage and what is going on after the rectifying bridge. So the Schottky diodes combined with the very low RDS on MOSFETs are giving us quite good results. So the circuit seems to work quite well. Next, let's check the inductor. For this experiment, I set the board to the side, prepared the wire with which we can short circuit the inductor. You're not supposed to work on live circuits though. And on the oscilloscope, we see the input current in green, and in blue the voltage after the inductor. So this is being probed by the blue probe. And while the output load is still at 1 ampere. So right now we can see our output ripple after the inductor. Maximum value of about 9.05 volts, minimum 8.16. And then the current, we have a maximum value of 3.14 amperes. So it's 1 volt per ampere. Now if we short circuit, we can see that the period of the current waveform slightly changes, so it becomes slightly smaller. And if we look at the voltage waveform, with the short circuit, the voltage is slightly higher, without it it's slightly lower. So unlike what the simulation was telling us, the inductor doesn't seem to be helping that much. Now there are two reasons for this. On the one side, my circuit has way more series resistance than the simulation circuit had, So we got series resistance in the capacitors, in the wiring, in the transformer. And secondly, the inductor itself is not made with ideal wire. It also has resistance. So in this particular case, with or without the inductor, we still get roughly the same current, roughly the same output voltage. Oh well. Now I put the circuit back together. It's on its rightful side. The wire was removed, so the inductor is still in the circuit. And next it's time to measure the output voltage and current performance. So just what sort of current can we pull from this circuit before we start running into various issues. So in green we have the current probe on the input. In blue we are measuring the output voltage, so this is set to AC coupling with 100 millivolts per division. And then we have our multimeters as before, output voltage, output current. So at 1 ampere everything works fine. But if I start to increase the current now, so we can see our input current is also increasing. And at some point, so at about 1.8 amperes, it's buzzing, that's not a good sign. We start to see an effect in the output waveform. So we are no longer supplying sufficient voltage to the linear regulator. It cannot regulate the output voltage. But if we go just a bit down, so 1.7 volts, everything looks nice and flat. So as you increase the output current, eventually the voltage drops on the various pieces of the circuit will be so large that you will not be supplying the linear regulator with sufficient voltage, so output cannot be maintained. To a certain extent, we could improve on this, making a fully active bridge, using an LDO with smaller minimum voltage drop, having less resistance in the various components, maybe fine-tuning the series inductor a bit. But in the end, you need to see the exact use case for your circuit. How much current do you actually need? So a typical preamplifier tube like the ECC83 uses 0.3 amperes. For a stereo amplifier, that adds up to 0.6 amperes. Now if the preamplifier has two such tubes, again a stereo circuit will draw 1.2 amperes, which is quite close to what we're getting. So this is achievable. But now if you want to supply the output power tubes, current will quickly rise. So a typical EL84 uses 0.76 amperes. So if you have two tubes per channel in a push-pull configuration, and well, stereo 2 channels, we need 3 amperes just for these. Higher power tubes, of course, will need higher filament currents. So what I'm trying to say here is that it might be a good idea to focus on what actually brings benefits. Sure, you can make a supply that will provide all of your tubes with DC, but the biggest benefit will be observed when you supply the preamplifier stage, since that has most of the voltage gain. Noise in that part of the circuit will be the most audible at the output. So it should not be that difficult to make a circuit that provides just your preamplifier with DC for the filaments. Anyway, I left the circuit running at 1.5 amperes, left it for about 10-15 minutes. Reason being, check its thermal behavior. So when doing this, first of all you'll need to leave the circuit run for a while, just so that the temperature stabilizes. And while afterwards we can proceed to perform some measurements. So to keep things quick, I will be using a thermal camera. So if we look at the circuit, we see two major hotspots. The linear regulator, we're expecting this to get hot, that's why it has a heatsink. But the other hot element is in the rectifying bridge. And if we just take a close-up shot, we can see that the main element that is heating up is the double diode component. So since this component sees most of the voltage drop, this is where most of the heat will be generated. Now in this case, I did not add any sort of cooling. That is because I wanted to leave the component to get a bit warmer, so that the voltage drop reduces a bit and power dissipation also gets reduced. Now if you go down this path, you should make sure that the component will not overheat overall operating conditions, since then the component might get destroyed. But anyway, other than these two major hotspots, so we were expecting these to a certain extent, the reason for looking at the thermal behavior of your circuit is to make sure that nothing else unexpected is heating up. And there's two main things to look for. If you add a series inductor like we did today, This might heat up if the series resistance of the wire is too high, so there might be high power dissipation on the wiring, or you might get core losses which also heat up the inductor. So these are some things that you don't want. The other thing to look for is the electrolytic capacitors. So because of the high ripple current that is going through them, and while electrolytics are known for having high series resistance, these can also heat up. Fortunately, in our case, these elements are not heating up, or at least not heating up by themselves. All of the heat that seems to be present on them is coming from the surrounding area. Now, if you suspect that any of your components are anywhere near their limits, you should make a far more accurate measurement using thermocouples. Thermal imaging, as long as you're not taking the necessary precautions, will be just a good indication, but it will not give you a definitive answer. Final thing to test out is the soft start behavior. Does that bit of the circuit actually work? So first off, I left the circuit as it is, so we have the capacitor built in, my active load is set to 1 ampere, and I set the oscilloscope to have 1 second per division. So this whole span is about 14 seconds. So if we take a single capture, turn on the power, wait for a while for the oscilloscope to perform the capture, so this takes about 15 seconds, and this is what we get. So we can see that our power jumps up to about 3.3 volts, and then slowly increases up to a plateau around 6.3. So as we have 1 volt per division, it takes about 8 seconds to reach the final value. Now, just to make sure that this actually works, I will now take out the capacitor and remeasure. So, capacitor has been removed, set another single capture, and when we turn on the power, well, we can already see on the multimeter that the multimeter died. But anyway, what I wanted to say was that the multimeter showed 6.3 almost instantaneously, and well, once the oscilloscope finished performing the capture, we can also see this on the waveform. So the input voltage jumped up straight to the final value, 6.3 volts, no startup, nothing, instantaneous output voltage. So this feature should help. But the real test is not really on the oscilloscope, but with a vacuum tube. So for this test, first of all I had to dim the lights so we can get a better view of the filament. I also tried to film it more close up. And regarding the measurement setup, I left the blue channel to measure the supply voltage, and with my current probe, this time I'm measuring the current going into the filament. So to observe if with and without the capacitor, if there's a difference. So first off, we don't have the capacitor, and if we try it out, we were able to see the flash in the filament, so there was an uneven heating up of the filament. And if we check the current probe, well, we can see that the current spiked to a peak value of 1.8 volts, so we had more than 1.8 amperes running through the 0.3 volt filament right at startup when it was cold. So now let's see if anything changes when we add our soft starting capacitor. So now I put back the capacitor, and if we retry our experiment, we now see a completely different story. So we see how our voltage increased really slowly, and we can also see peak current at about 1 ampere, so 106. So by adding in the soft start, even though it didn't start off from 0, we managed to almost half the peak current that the filament sees. So this sort of measure should help with expanding the lifespan of your vacuum tube. In the end, the circuit works as expected. We are getting our 6.3 volt DC from 6.3 volts AC at a decent amount of current. But even so, when designing a circuit, this is not always the case. Just because it worked well in the simulator does not mean it will be the same in real life. Most often, the reason behind that, when performing simulations, various parasitic elements are neglected, and the component models are simplified to ensure a fast simulation time. So practical verification and fine-tuning is always necessary. And with that said, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.